Our next example asks us to find the work done by this vector field in moving a particle along this line segment. And so here they don't actually give you the line integral symbol, but that's okay. We know that the work done, we can interpret, the work done by the vector field as the line integral along C of f dot dr. It's always nice to write down what we want symbolically, and now we know that we can translate this to the integral from 0 to 1 in our case of f of r of t dot with r prime of t. Now typically you're not given the parameterization. I went ahead and wrote that down just to save time. Just a line segment starting here, going there. Make sure you can do that. Maybe pause the video and make sure that you can come up with this yourself. Okay, so now at this point, I'm just plugging and chugging. Here we go. I'll go down here and write this as the integral from 0 to 1. Okay, plugging in my parameterization into f. I got to squeeze up, try to get this all on the screen. There we go. Interesting how y shows up twice. We can do that. So let's see. We're going to have y is 1 plus 2t. And then I want x plus z. So what's that going to be? 6 plus t, when I add x and z together, adding this and this together, and then y again, 1 plus 2t. I'm going to dot with r prime. That's just going to be the direction vector. So what, 6 to negative 5 dt. We'll take this just one step farther, and we can write this as the integral from 0 to 1 of, oh goodness, I don't really want to do this, 6 plus 12t, and then let's see, plus 12 plus 2t minus 5 minus 10t dt, and we might as well combine 0 to 1. 6 and 12 is 18, minus 3 is what, 13, minus 5, excuse me. 12 and 2 is 14, minus 10 is plus of 4t, and when I worked this out, I came up with 15. So I'm going to hope that I did all my algebra and arithmetic right, and you should be able to work out 15 from there. Okay, so I thought I would show you a picture of what this actually looks like. Unfortunately, this is made in Mathematica, but unfortunately I can't spin it the way that we did in Mathematica to help you see. But here we found the work done to be 15. So that means the vector field is actually moving. The particle is starting here and it's going down this line segment, so it's going like this, and the particle is actually pushing, and you can kind of see the arrows seem to be going that way. Actually, if you could spin it, you would also see that they're pointing up a little bit. And so looking at a vector field at a glance, it can be a little tricky to tell whether the work done is going to be positive or negative. You actually need to compute the integral to tell, because you can't tell. Maybe we're fighting against it in the z direction, but we're gaining more in the x direction than we are losing in the z direction, which in this example is indeed the case. But that's kind of a picture of the sort of thing you're computing. This vector field is like this sea full of these vectors, and then you've got your little curve in there, and you're just computing the line integral of the vector field over that curve, and you can interpret that again as the work done by the vector field in moving a particle along the curve. So I'll end this video series with a couple of comments and then just one last example. I think we'll combine this into one video. So I wanted to show you the connection between line integrals of vector fields and then line integrals with respect to x, y, and z. So this will just take a moment. So I'm going to assume I have a vector field where the component functions are p, q, and r. Each of these is a function of x, y, and z. We know that the line integral of f along c is integral f of r of t dot r prime of t. I'm going to actually write that down. So this is, you're plugging in r of t into each component. So p of r of t, q of r of t, r of r of t, dot with r prime is x prime, y prime, z prime. Okay, we can take the dot product and you get p of r of t x prime, q of r of t y prime, r of r of t z prime. But then I want you to realize that if we started here and went backwards, you could see these are the same. That's exactly the integral of p dx plus q dy plus r dz. Let's just do one of these. Let's do q dy. if I want to do the integral along C of q dy, I would say it's the integral from a to b of q of r of t times y prime dt, which is exactly what we have. So it turns out that if you add up the line integral along C of the component functions, p with respect to x, q with respect to y, r with respect to z, then you do indeed get a line integral of a vector field. So I said at the beginning, these individually don't have a nice physical interpretation, but they're a part of line integrals of vector fields, which you can interpret as work. So just a quick example of how one might do this. I'm not actually going to compute anything, but if you started out with this integral and you wanted, you could rewrite this as the line integral of a vector field f, where what's f? Well, the first component of f is x sine y. There is no y here, it's 0, so we just put a 0 for the y component, and then an x, y, z, dz. And I've actually got this jotted down. Give me just a second here. I've got this numerical solution for this problem. I'm not going to work it out on the screen, but for those of you that are needing something to do, which I'm sure is all of you, you're going to get minus, actually let's put it up here. You're going to get minus a half times cosine of 1 plus, I can't read my own writing. It looks like I wrote 5 over 0, and that's not what we want. That would be very bad. I think it's 5 over 6. I'll put a question mark there, but you can work that one out yourself if you want to. But I just wanted to show you how you can go from this sum of the line integral with respect to x of this guy, line integral with respect to z of this guy. You can rewrite that as a line integral of a vector field where that's your vector field. That's the takeaway here, and I think this is what you get, but I can't read my writing. It looks like 5 over 0, which I know can't be the case. So, all right, we made it through 13.2. Great job. The next couple of sections won't be this long. We're going to be looking at some nice results. Basically, we're going to learn line integrals, and then we're going to learn surface integrals, and then we're going to learn some theory that allows us to go back and forth and convert different things, different line integrals and surface integrals to either double integrals and triple integrals. So that's where we're going. This section, this chapter, tends to go relatively quickly once we get into it, and so this is probably in some ways the biggest section because we needed to introduce all of these pieces. I've got some handouts I'm going to be posting to try to help you keep track of everything, but you've got what you need to do.